maybe one thing that I did promise last time was that I was going to do the fundamental theorem of algebra again. So maybe let me do that. Okay. So so remember we had Liouville's theorem. Okay, so Liouville's theorem said that if f from C to C is analytic and bounded, then f must be constant. I mean, if you think about this, this is an insane result, right? It says that, over the reals, this is definitely not true, right? Just take, maybe it's worth making this even a stronger point, right? Not true in real analysis. Right? Just take, say, f of x equals sine of x. Right? It's a very nice function, sine of x. It's bounded, right? Sine of x is never smaller than -1 or bigger than +1, yet, of course, it's not constant. Right? So complex numbers, functions that are analytic over a complex plane are very special. We had seen versions of how special they are when we saw that, right, if you can differentiate once, you can differentiate actually as many times as you want, right? This was a version of being special. But that felt as sort of a smoothness type condition. Right here is somewhat different, right? Because it's not just that the function is very smooth, actually needs to shoot off to infinity, some direction, unless it's, unless it's constant, right? And so then from this, we could get the fundamental theorem of, the fundamental theorem of algebra. Which, right, amazingly is proved with analysis. Right? So if, or I should not, no need for if, every non-constant polynomial has a 0 in C. Okay, so C is algebraically closed. Right? Any polynomial over C needs to have a 0 unless it's a constant. Okay, and we prove this. I mean, I did this a bit fast, so I'll do it again because this is such a, it's one of the coolest implications of complex analysis, right? So let's say, let P of Z be an unconstant polynomial. Constant polynomial. Okay, now suppose or assume, let's assume that, right, we're going to go by contradiction. Let's assume that P of Z has no zeros. Right? So if P of Z has no zeros, the idea is that 1 over P of Z is nice. Right? So 1 over P of Z is analytic, of course, because P of Z has no zeros. Also, it's not hard to argue that 1 over P of Z is bounded. Okay? I mean, we can do the actual calculations to argue this. Let me see if I can convince you with enough rigor that you're convinced, but not enough that I spend 15 minutes doing estimates, right? So why is this bounded? So let's prove this. So proof of this fact. Okay, so take P of Z, right, is equal to some an z to the n plus an minus 1 z to the n minus 1, and so on and so forth, all the way to a 0, right? With an not 0, right? If an was 0, then we would just, right? If n was 0, then the degree would just be n minus 1, and we would take this to be n, right? So an is not 0. Okay? So now the claim is that P of Z, right, there exists some radius r, right? such that P of z is bigger than some epsilon for, or like, let's say there exists, I mean, we can even start with there exists epsilon and there exists r, such that P of z is bigger than epsilon for every, or in absolute value, for every z, such that the norm of z is outside this radius. Right? Why? I mean, it's easy to see, right? If I start making the norm of z very big, right? Okay, let's just work out another thing, right? So we definitely have that P of z is bigger or equal than, right? Just triangular inequality. A(n) z to the n plus, right, say, minus, sorry, right, say a n minus 1 z to the n minus 1 plus all the way to a0. Okay, so far so good, right? So, you know, the absolute value of this needs to be bigger or equal than the absolute value of this minus the absolute value of that, right? Just triangular inequality if I were to move this over there. Okay, but now just take, right? Let's say that let's take r to be bigger than 1. Okay, because I just need for it to exist 1, right? So let's take r bigger than 1. And the bigger the r is, the more, right? The more easy to satisfy is this condition, because the less z is there to satisfy this condition. So if I take r bigger than 1, then right, P of z, right, will be bigger or equal than a(n), right, z to the n, say. And then this can only get bigger if I swap every single term, right? Here there's a term z to the n minus 2, and here there's nothing, but actually z to the n minus 1. So I could do this. Let's say minus 1 z to the n minus 1 plus, you know, a n minus 2. And then I still keep z to the n minus 1 all the way. I mean, I'm of course losing a lot in this argument. The point is that I just need to show that it's bounded. I don't need to show that it's bounded by, you know, I don't need to have a good epsilon and a good r. I just need to show that it's bounded, right? Z to the n minus 1. Okay, so in particular, it's bigger or equal than a n z to the n minus, you know, z to the n minus 1 times, say, the sum of, right? This is upper bounded. I just need to give an upper bound on this, right? So that when I have the minus sign, it's a lower bound. I just have the sum of the coefficients an. This is just, right? I can just write as the sum, you know, n times the biggest one, right? The max over k of ak. Again, losing everywhere, but that's okay, right? And now, I mean, we're essentially done, right? Because I can move the z to the n minus 1 here, and now I have an. Let's actually put even the an here. Okay, bigger or equal, and now I just have norm of z minus this term minus n times max k ak, and now divided by an. Right? We make this a bit nicer looking. No, this is just, yeah, 1z. Yeah, let me just make this a little nicer looking. Okay. There's an z to the n minus 1 times this, right? But I'm taking r bigger than 1. I just have to take r as well. Like, I just have to take r bigger than this. Let's say twice this. Right? Max of ak over an. Right? And if I do this, then of course, you know, if I take r bigger than twice this and r bigger than 1 or even than 2, then of course this is bigger or equal than epsilon for some epsilon. Okay, so what I just showed is that, right, there's some epsilon and some r such that this is bigger than epsilon for every z, right? Just how you imagine polynomials, right? If a polynomial eventually only the z to the n term matters, and that one goes to infinity, right? So of course at some point the function needs to start growing. Okay, and so what it means now I can look at, right? Now I can look at the minimum of the. Maybe I'll erase Liouville's theorem. I'm almost done, but. Okay, now I can look at the minimum, right, of P of z in z inside the ball of that radius. So z such that z minus 0 or just the norm of z smaller or equal than that r that I picked, right? Right, because this set is compact, right? Because the ball, the closed disk is compact, right? And P of z is continuous, right? It's a polynomial. The absolute value, is continuous. The absolute value is continuous, right? Then it has a minimum. And it's not 0, right? Because if it was 0, then the function has a 0, right? And it can't be 0, right? And so, P of z is always smaller, is always bigger or equal than the minimum between that epsilon that I picked and this minimum that I know exists and is not 0, right? Minimum z z such that norm of z smaller or equal than r, right, of P of z. Yes. Right, so this is strictly bigger than 0. Right, and this is something that doesn't depend on anything. We can call this, epsilon prime. Right, and so 1 over P of z is bounded. Right, and since 1 over P of z is bounded, right, then by Liouville theorem, it's constant. And this is a contradiction, right? Because we said P of z wasn't constant, right? And so this proves, right? This proves the fundamental theorem of algebra, right? Every non-constant polynomial needs to have a 0. Okay. Maybe you remember when I said back in, back in the start, maybe the first week even, that basically analytic functions were going to be essentially like polynomials in a certain way. And the way that we're going to prove the fundamental theorem of algebra was by saying, if a polynomial doesn't have a 0, then 1 over that polynomial is still nice, right? It's still analytic. Because analytic functions are a bit like polynomials, it will have to, right? 1 over P of z doesn't go to infinity, and polynomials need to go to infinity. The only way this could have happened is if it was constant, and that would mean the original polynomial was constant. Right? If you can see, this is sort of what happened, right? We're using the fact that 1 over Pz needs to behave like a polynomial in the sense that after a certain ball, it needs to shoot off to infinity. Or, P of z needs to shoot off to infinity, so 1 over P of z, right? Because it's analytic, it's, right? It doesn't actually shoot off to infinity like a polynomial would. It's bounded, and so it actually needs to be constant by Liouville. Okay, so what I said, right, a few weeks ago was very hand-wavy, of course, but this is sort of what's at the core of this argument. Okay, all right. Any questions about the fundamental theorem of algebra? So now in algebra class, you don't have to trust that polynomials have zeros. Okay, so now I'm going to continue with showing more ways in which analytic functions are like polynomials. Okay, so now we're going to do some more analysis and take out some more implications of the Cauchy integral formula. Okay, so let's recall. Okay, so like recall, just because it's good to have this formula on the board always. Theorem, so suppose like let F be analytic in an open disk. Gamma closed curve right, a closed curve in the disk, right, for any z such that the curve goes around z once, right? We have f of z is the integral of f xc, right? And now it's xc minus z. Okay, I made a few typos last time in which I wrote z minus xc because there's this change of variables to, you know, like switching the z and the a by the xc and the z, and so this happens a fair amount. But the formula is the thing that's being over the curve minus sort of the thing that you're integrating as thinking of the center. Okay, so this is the Cauchy integral formula, right? And we often take the curve to be a circle, right? That's when it's, you know, that's when it's really useful because, I mean, it's also useful, of course, with any curve, but the nice thing, the really powerful thing about this theorem is that it allows you to describe the function at a point z by values around it. And because the set is open for any point z, there's always a little ball around it. So you can always draw a circle around it and then do this theorem for the circle, right? And we also have this formula for the derivatives, right? In which this is equal to fc. Okay, let me do it over the circle. Doesn't really matter. C minus z. Oh, I forgot the 2 pi I. Typical. Let me make sure I get the. There's an n factorial. 2 pi I n plus 1. Right, this plus 1 was missing in the other formulas. Okay, and the way to show this is just you differentiate this over and over again. Right, if you can differentiate inside the integral, you would get exactly this, and you just have to argue that you can differentiate inside the integral, and we did this last time. Okay. Now, the really nice thing, right? So the idea for today, I mean, in a way, okay, this is the key idea for today. Right? We're going to, you know, make this idea more precise and use it a lot and so on. But the key idea is that even if f is not defined at a certain point, say a, or let's say that f is not defined at z, right? So let's say, okay, a bit of intuition before I start writing formulas. Let's say that I have some kind of region, right? Or a disk, doesn't matter. And I have some point a where f is not defined. right? So it's what we call a singularity, right? So there is some singularity there, but F is nice and defined everywhere. We saw that some types of singularities were okay. Cauchy's theorem would still work, right? If the singularity was like, we call these exceptional points, right? If it satisfied that the limit as z goes to a of z minus a times f of z was 0, then for most of, for all the Cauchy theorem type consequences, this was perfectly fine, right? But still, f of a is not defined. But let's say that we have such a function where it's not defined on a, right? This is screaming at us that maybe what we should try and do, right, is use Cauchy's theorem, right? We could try to use Cauchy's theorem, this integral formula, put a circle around here somewhere, right? And now once we have a circle around here, we would expect that f of a could probably be defined as the integral around that circle, right, by that formula. Right? It's a reasonable thing to think, right? Because, I mean, as long as f is defined on the circle, on the curve, then this formula makes perfect sense, right? And because Cauchy's theorem was true even with these special types of singularities, we can definitely try to define f that way there, right? And so what this formula allows us, oh yeah, it is. Thank you for the, I keep forgetting the 2 pi I, sorry. Okay. So this formula not only allows us to talk about regularity of the function by saying something about the values of a curve around it, right, which enforces a lot of smoothness, but actually lets us sort of extend functions to points where we didn't know what the function should be there. And this is going to be the key idea for today, right? So I'm going to make this a bit more precise, and then we're just going to keep taking consequences and consequences of this, right? And it's going to allow us to talk about different kinds of singularities and essentially completely characterize the type of singularities that analytic functions can have. Or, I mean, functions are analytic everywhere except the singularity, of course. Okay, so that's the plan for the rest of, well, today probably, actually. Okay, if any questions, please interrupt. Okay, so we don't need this anymore. Okay, so this formula, right? So Cauchy, like Cauchy's integral formula. Right, still holds. I mean, the proof, right, was everything was the same. We still holds as long, right, as long as still. Oh, this is not what I should have written. Sorry. So holds for even if, let's say, let me write that this. If f has singularities, aj, right, for some, right? So what I mean is f is analytic, right? F is analytic in, right, say the disk, except these points aj, right? Provided that, right, the same condition as before, right? The limit as z goes to one of these points, is 0. Okay, and the proof is exactly the same as, right, the same as before. Okay, provided, of course, the curve is not, right? Provided, I mean, okay, I should say, as long as, for right, as we prove this formula, of course, as long as, right, the A's, right, AJ is not in the curve for any J, right? Otherwise, we can't make sense of the formula, and Z can't be AJ either, right? Because I mean, this is a formula about f of Z being equal to something if f is not defined, and Z being different than AJ for all J2. Right? And the proof is exactly the same as what we did, right? Whenever we proved, you know, Cauchy's integral formula and Cauchy's theorem and so on, these points were never a problem, right? Because when we did, this goes back to the fact that when we did this bisection argument, the integrals also still converge to 0 around the neighborhoods where there's these singularities. Okay, so these types of singularities are not a problem at all. Okay, and so what this allows us to do, right, is this allows us to now define, right? So now what this allows us to do is to say, right, we take, like, let's say that, let me go back to white chalk. Make sure I don't forget to say anything important. Okay, so let F be analytic in a neighborhood of A. Okay, so what I mean by this is there exists some delta bigger than 0, right? We're now going to use this to argue about local properties of analytic functions. Okay, so let F be analytic in the neighborhood of A, meaning there exists some delta bigger than 0, right? Such that F is analytic, right? F is analytic in the set Z such that Z minus A is smaller than delta and not 0, right?
Excuse me?
Yeah?
Well, I cannot, and some people in the chat cannot read the end, as long as the end of the second script, as long as AJ is not in gamma, and then...
for any J. Yeah.
And Z equals AJ?
And Z is different, and different, sorry. Yeah, thank you. Okay, I'll rewrite this.
Perfect.
Right, just because we need to be able to make sense of this formula, so, right, because F isn't defined in any AJ, neither Z nor C can have any AJ. So I'll write here in a more precise way. Okay, so, yeah, as long as, let's say, the AJs, maybe this is better, intersected with the curve, intersected with the, let's say, let me not try to be lazy, is 0, and the AJs intersected with Z is also 0, is also empty, right? I mean, this is maybe the most precise way of writing, right? Because I need to make sense of, like what I said intuitively is that we can define f of A to just be set Z equals A, but the theorem here is that the formula still holds. But to say that the formula still holds, I need to make sense of both the left-hand side and the right-hand side, right? So neither the curve nor z can be in the exceptional points. Okay, but now let f be analytic in the neighborhood of a, right? Such that it's analytic right? Such that it's analytic in in the neighborhood not necessarily of a, in a, right? If the limit z goes to a, right, of z minus a f of z is 0, right? Right? Then the Cauchy integral formula will hold. So let me draw a picture, right? So we have a, right? F is, we don't know what f is at a, but we know that f is analytic in the neighborhood. Okay, so we're going to take like a neighborhood, right, at distance delta. And we know that f is nice in this neighborhood, right? We don't know the value at a. What we can do is we can now take a circle, right? We can take another circle, right? A circle around a, or I mean, it doesn't need to be centered in a, but anywhere. So a circle such that, a circle inside, like inside the neighborhood, inside the neighborhood. Right? So now Cauchy, because f is analytic in the pink region, except for this exceptional point that satisfies this limit that we know then becomes not a problem, right? Then the Cauchy integral formula, right? The Cauchy integral formula, right, is valid in C, right? So in particular, or for C, I should say, right? So in particular, for any z inside C, right, inside this smaller circle, so right, in this yellow region, for any z in this yellow region, but not a, we must have that f of z is equal to 1 over 2 pi I integral over the circle of fc c minus z. Right? Okay, just because of this, right? The Cauchy integral formula holds even without these bad points, because we saw these bad points are not really bad from the viewpoint of, right, from the viewpoint of Cauchy's theorem. Okay, but what does this tell me? Now, because we proved that we can differentiate inside the integral, right? We did this last Friday. Right? We actually know, let's see if I'm more show. Right? Because we proved that we can differentiate inside the integral, we know that, the function, let's call it, I don't know, g. G of z equal to 2 pi I C f right is analytic inside C, right? Because we know, I mean, the dependency of this on z is just here. This is a continuous function on the circle, and we showed that, a formula of this type where this is a continuous function in the circle is analytic, and we even calculated its derivatives, right? When we differentiate, n times just shows up an n factorial here, and this power to the n, right? So this, and of course, obviously, because of what we saw there, g of z equals f of z for all z not a inside the circle, right? Just inside the circle. Right, so what does this mean? This means that there exists a function that's analytic in the circle, inside the circle that equals f of f in the neighborhood of A, and we know what the value is for A, right? The value for A is just this formula, right? So f can be extended to an analytic function right, can be extended to an analytic function by taking f of A equals to 1 over 2 pi I c f of xc over xc minus z dxc. Okay? And so, right, what we saw here is that if f is analytic in the neighborhood of A, and but it's not, maybe not defined on A, then actually if A satisfies this, we can remove it, we can define it on A. Okay? So let me write now a proper theorem, right? It will just be recalling of all that we wrote. Okay, so let me write now a theorem. Let me try to decide what I'm going to erase. I'll erase these two boards. Okay, the only thing that I didn't do is I didn't redo the proof of Cauchy integral formula with these points, but it's kind of clear, right? Because of how the proof of Cauchy theorem went. You remember that in the proof of Cauchy theorem, these exceptional points didn't matter at all, and it's exactly the same proof. Okay, so let me now write the theorem. Okay, so theorem. If f is analytic in a region, right, omega prime obtained from omega by removing a point A in omega. Okay, so it's analytic in a region. I now made a hole, took out A, right? Exactly this picture, right? I mean, I try to draw as many pictures as I can to make things more clear, but let's say this is a region, right? I went and I took away 1 point. Okay? This is my point A. Now I know that f is analytic in the region obtained by omega minus the point A, right? Think like 1 over z, where the point would be 0, right? It's analytic in a region omega prime obtained from omega by removing A, right? If the limit, right? Because A was in omega, there is a neighborhood of A is inside, there is a neighborhood of A that's inside of omega. So I can talk about limits going to A. Then, now, I'm not sure what language to use, but if this happens, then f can be extended to a function analytic in all of omega. Yeah, then f. I don't know if yeah, it's okay. I'm kind of reluctant to use the verb to extend, but I think it makes sense. Then f can be extended to an analytic function. To an analytic function in all of omega by taking f of A to be equal to 1 over 2 pi I C f of c minus a dx c, where c is a circle in a neighborhood, a circle with a inside and contained in a neighborhood. Of A. Okay. Oh, I realize you probably can't read anything where C is a circle. I mean, it's kind of clear what I mean. It's just I need to write a lot of words. Okay, but maybe I'll. I'll write another color because it's really not as important, but okay. Where C is a circle such that A is the inside of C, and C and inside of C are in omega. Right? I mean, it's exactly this picture, right? It's just by words. I need to by words say what the picture is, but it's exactly this picture in which I take a circle that's inside omega, right? There's always, because omega is open, there's always, well, someone asked if it has to be a circle. No, it doesn't have to be a circle. It has to be, though, that it loops around A exactly once. We just take it a circle because then it's easier to argue, right? Right, the point being that, you know, if it's an open set, you know that it's always a ball around it, so you just put a circle around it, right? The point here is that it allows you to say things about the local nature of F, and so a circle is just as good as any other, as any other curve. Okay, so this is the theorem, right? By now it's proven, right? And then sort of made sense. Now we call this a removable singularity. Right? Because it's not really a singularity. Right? These are not real singularities. Right? Because actually, actually we just showed that the function is actually analytic. Just, you know, when we're given the function, someone forgot to tell us what the value was at A. There's really nothing special about A. But of course, you know, if you think about 1 over Z, it doesn't, right? 1 over Z cannot possibly satisfy something like this. Right, so think of f of z equals 1 over z, right? It's not. I can't just remove the singularity at 0, right? But on the other hand, it also doesn't satisfy this, right? But it's already saying that you cannot have things like 1 over square root of z, right? I mean, because square root of z has the issues with the branches. Okay, so I guess it's already 11, so we'll stop here, and I'll come back in 15 minutes, and we'll do the, we'll now use this. Basically what we're gonna do, I mean, as a foresight, is we're gonna use this theorem now on the approximation of the derivative, just like how we prove the Cauchy integral formula, actually, right? We're gonna use it on like fz minus f of a over z minus a, and we're gonna start taking, you know, this is gonna allow us to define things that look like approximations to derivatives and get something that looks like Taylor expansion. Okay, so we'll see it in 10 minutes or so.